Welcome! This is the first video for Unit 4, and this one, as you can probably tell from the title, covers momentum, impulse, and the momentum impulse theorem. Let's get right into it here. So, momentum is just another way you can describe like an object's motion, and like I guess you can think about it, it's like its tendency to go towards a different direction. That's a little scuffed. I wouldn't really think about it that way. I think if you really want to consider momentum with like an actual definition, we could look at it from a mathematical standpoint. The variable for momentum is, interestingly, it's p. I don't know why it's p, but it's p. This one's a vector value, so I'm going to indicate that. P is equal to the mass of an object times its velocity, and that's also vector, which is why momentum is a vector. As you can tell from here, the units for momentum are kilograms times meters per second. There's another thing very closely related to momentum, and that's impulse. Impulse is represented by the variable j. It's a vector value. And the impulse is equal to force times time. Or like alternatively, force times the amount of time that force is applied for. And the interesting thing with these two values, oh wait, no, I forgot to hit the units. This one, as you can tell, is Newton times seconds. Pretty straightforward. So momentum and impulse. And the interesting thing about these two quantities is that they're actually equal to each other. Now, why is that the case? Well, for this one, let's revisit good old Newton's second law. Newton's second law, as you may recall, states that F is equal to m times a, where the force is equal to the mass of an object times the acceleration of said object. Now, as we know from our kinematics equation, v equals v naught plus at, we can rearrange this to solve for a. We would have v is equal, nope, wrong thing, v minus v naught is equal to a over a times t. Divide both sides by t, and then a is equal to change in v over t. So I'm going to substitute this in. I have force is equal to m times change in velocity. This is technically a vector value. It's a bad arrow. Over t. And now I'm going to multiply both sides by t. Ft is equal to m times the change in v. And that's a vector. As you can see on this left side, we have impulse. That's just force times time. And on the right side, this technically isn't momentum, so I technically lied to you earlier. This is actually the change in momentum. This I can just translate into j, or impulse, is equal to the change in momentum. This is what we call the Impulse-Momentum Theorem. It's basically just saying that the impulse is equal to the change of momentum. Pretty straightforward. However, as you can see from this Impulse-Momentum Theorem, the units of newtons times seconds equals kilograms times meters per second, because those were the units of impulse and momentum respectively. If impulse and momentum are equal to each other, then those units must also be equivalent. Now, there is something else that we can use with impulse. If we have a force times time graph, that's a bad graph. Okay, that's a little better. Force in newtons, time in seconds. The area under the curve for a force times time graph is going to be the impulse, because, newtons times seconds, that's just impulse. Alternatively, we could also think about that as the change in momentum. So let's do a quick little practice here. Let's say 10, 15, we'll say that's 5, that's 0, 20, 25, I can stop that there. Then 1, 2, 3, 4, 5, let's extend that a little, 6. Let's say I have a graph here. It goes like this, and then it shoots up to 20 there, stays at 20, goes all the way down to 5, and then let's say it goes down there. Looks like I didn't need to expand that then, huh? Okay, I'll just erase that. And you know what? Well, I'll just erase up there too. And, okay, why is there a random dot there? Let's say this force is acting on a 6 kilogram object, so mass is equal to 6 kilograms. Now, say it's initially going at 3 meters per second. V naught is equal to 3 meters per second. What's the final velocity here? Well, for this one, you would opt to use the impulse-momentum theorem. We know that impulse is equal to the change in momentum, and like I said, the area under the curve for a force times time graph is equal to the impulse. So let's look at this area here. I'm going to chunk it up into a few different sections. I'll have, I'll use a different color for this. This area, I'll chunk that up. There. Okay, now that just looks like 2 chairs. Like, it's not just me. 2 chairs. Anyway, that's 1 times 10. So this region is 10. This is 1 by 10 as well. So this one is 10. This is a 1 by 10. But this is a triangle. So that's going to be 1 times 10 times 1/2. This part is 5. This whole thing is 20 times 1. This section is 20. 5 times 1. This is 5. Did I screw the math up somewhere? No, I think I'm just gaslighting myself, huh? This is 15 times 1. Well, so 15 times 1 times 1/2 is 7.5. And then this little area down here is 1 times 5. 5 times 1 times 1/2, 2.5. Okay. Let's add this up here. We have 10 plus 10 plus 5 plus 5 plus 20 plus 7.5 plus 2.5. Let's see, that's just 20, that's 10, that's 10. Easy numbers, nice. That's just 60. So our impulse is 60 here. So we have 60, and that is equal to our change in momentum. Here I'm going to rewrite change in momentum as our m times velocity minus initial velocity, because this makes it easier to solve for v. Because here I can just divide both sides by m, and then add v naught to both sides. And then now I can just start throwing in numbers. 60 over m, well, m is 6, so 60 over 6. My initial velocity was 3, that equals v. So this is just 10 plus 3 equals v. V equals 13 meters per second. This is crammed in the corner. Oh well, who cares? You get the idea. Let's do one more here. This one is also going to use the impulse-momentum theorem, but instead of solving for final velocity, we're going to solve for something else this time. So, let's say I have a force that has a magnitude of 20 newtons. And this force is slowing down a 4 kilogram object. It goes from 15 meters per second down to 7 meters per second. How long was this force applied for? Well, like I said, this one uses the impulse-momentum theorem. So J is equal to change in P. I'm going to expand this out here. Force times time is equal to m times v minus v naught. My force is 20 times t is equal to mass, that is 4, times final velocity is 7, initial is 15. However, here, there's actually something that you might want to do. Since we know that this force is slowing the object down, that means the force has, it's going in the negative direction. And since force is a vector value, we are able to attach this negative onto that 20. So yeah, that works out for us. Anyway, here we have 4 times negative 8 is equal to negative 20 times time. That is a really bad t. That's a little better. 20 times time, negative 20 I should say, is equal to negative 32. I have time is equal to negative 32 over negative 20. That simplifies to, I can do this in my head, 10, 16, 1.6 seconds. That's our answer. So using the impulse-momentum theorem, we have determined that this force of 20 newtons was applied for 1.6 seconds. Impulse-Momentum Theorem is a really useful starting basis for like a lot of these impulse and momentum problems because of this really like this relationship, the fact that impulse and momentum are equal is like a lifesaver when it comes to these problems because like it makes it a lot easier to do these types of problems. Anyway, I will see you in the next video. Next video we will be talking about collisions and the conservation of linear momentum. I'll see you there.